Okay, just a detail here about the fact that when we're talking about rates of reaction, it can be a little bit tricky for us all to agree on our rate of reaction if we don't know what species we're focused on. Imagine this reaction here where nitrogen and hydrogen gas are coming together to form ammonia gas. And what you'd think is, well, if I look at this reaction rate from the hydrogen gas's perspective, it's going to look a lot faster than if I'm looking at the nitrogen gas, because for every one nitrogen gas I use up 3 hydrogens. So how can we all agree upon the rate of reaction? Well, the easy answer here is we're going to state the rate of reaction for one species or for the overall reaction, and we need to be clear in that when we're asking one thing or the other. So we're going to, as an example here, let's assume at one instant the rate of the concentration of hydrogen gas is being reduced by 0.6 molarity per minute. So my rate is 0.6 molarity in 1 minute or 60 seconds. So let's just reduce that to 0.6 divided by 60, 0.01 molarity per second. So that was my rate for my hydrogen gas. If I want to know my rate for anything else or the overall reaction, all I have to do is use my mole ratios. If I have 0.6 moles of hydrogen gas, I can recognize that I can set up a ratio between moles of hydrogen and moles of, say, nitrogen. That they would be in a 3-to-1 ratio. Well, since this is moles per time and the time is common, this same ratio can be used for the rates. So since time is constant for both, if this is the ratio of the moles, this is also the ratio of the individual rates for the individual species. So, for example, if I want to find the rate of consumption of nitrogen gas, and I have that of hydrogen, I can say that the rate for nitrogen gas versus the rate for hydrogen gas is in a 1-to-3 ratio. So, if my rate for hydrogen gas is 0.01 molarity per second, my rate for the nitrogen gas would simply be, that should be 1-to-3, not 1-to-2, 0.00333. That's the repeating one, molarity per second. That would be if I wanted nitrogen gas. If I wanted the rate of ammonia gas in comparison to the rate of hydrogen gas, I would just be using my 2-to-3 ratio. So here my rate here we're dealing with ammonia gas here, is going to work out to be 0.00667 molarity per second. If I'm interested in the overall reaction, what I assume is if I wanted to write my rate off to the side, rate equals blah, and I don't want it to be associated with any one species, I would have to imagine that I have a coefficient of 1 sitting on that rate. So if I want to do hydrogen gas to overall reaction rate, then I would just put in a 1 for the overall reaction rate's coefficient when setting up my mole ratio. We've already done this one. Since nitrogen is 1, then the rate for the overall reaction, the rate for the nitrogen would be 1-to-1. So we know that the rate for the overall reaction is going to be 0.0033 molarity per second. So the rate of reaction does depend on what species we're paying attention to. Since the different particles might react in different ratios, we have to take that into account when we're considering our rates of reaction. The rate of hydrogen gas here is faster than the rate of ammonia or nitrogen because there are 3 hydrogens in the recipe and only 1 nitrogen in the recipe and 2 ammonias in the recipe. We can take that into account just like we did in stoichiometry using our mole ratios and use the rate of any one reactant or product to figure out what the rate of the other reactants or products would be.